Nair group, Atul Vijay, now who is working in BL, Anshu Jain, Ritin MR, Joseph Lawson. These are all mainly contributed. These are the main contributors, my students here and abroad. And some of the work we are also doing in collaboration with Dr. Hemant Kumar, Associate Professor, Mechanical Department, NIT Surathkal. Few slides I have taken from collaborative work, and I will mention wherever it is, wherever I have taken those slides, I will mention it to you. So I'm grateful to these contributors and my both UG, PG, PhD students. With this sense of gratitude, we will start the smart materials and its application. Basically, smart material, before getting into the smart materials, let us try to have a overview of the types of the fluids. All of you know that there are many types of fluids are there. Ideal fluid, which is incompressible, it has no viscosity, no surface tension, no compressibility. It's called ideal fluid. That is x-axis in this diagram is the ideal fluid, which has no, which is incompressible, which has no viscosity. And there is no ideal fluid as such in this world. All real fluids, including water, possess the viscosity, surface tension, and compressibility. So all practical fluids are real fluids. A real fluid actually which obeys the Newtonian laws of viscosity, that is tau is equal to mu into the dou u by dou y, or du by dy, you can say in one dimension. So are called Newtonian fluids. That means the shear stress is directly proportional to the shear strain. Such a fluid are called Newtonian fluids. And if they don't obey the Newton's law of viscosity, that is the shear stress is directly proportional to the shear strain rate, then such a material are called non-Newtonian fluids. And there are, in this class itself, we have a dilatant fluid and pseudoplastic fluids. A dilatant fluid, the viscosity increases with the rate of deformation. It's also called as a shear thickening fluids. For example, if you have this baby milk powder, and if you churn with the spoon, after churning, what happens? If you shear, that is, the churning is a shearing process. If you churn that the baby milk powder, it becomes thick. So this is a very good example of shear thickening fluid. Earlier, when we put the milk powder and milk or water, it is a fluid. Okay, non-Newtonian fluid. But if you turn, if you shear it, then it becomes a shear thickening fluids. For example, if we design the military, military jackets with the shear thickening fluids, and as soon as this the bullet comes in, and if this fluid is able to capture that bullet inside that the shield, then that bullet will not enter into the soldier. So there we can use a shear thickening fluids. And another, obviously, the velocity decreases with the rate of deformation. Such a fluid is called shear thinning fluids. The blood is actually a shear thinning fluid. A Bingham plastic fluid is also ideal plastic fluid. If you see this above here, can you see my arrow mark, please? Can you see my arrow mark, whatever I am showing cursor? Hello?
Yes, sir.
Okay. So if you see this pseudoplastic material, the ideal plastic material, it is also called as a Bingham plastic material. Bingham plastic material, that is some yield stress, some yield, external yield force or yield stress is required to cause this flow. Here, there is no shear external force is required to cause the flow. But Bingham plastic, the certain initially the yield stress is required. After that, the stress is proportional to the rate of shear strain. In fact, this is actually the power of N, and that N is equal to 1 for the Bingham plastic, and this N is equal to 1 for Newtonian, and this is just plus tau y for this Bingham fluid, because this tau y is added for the Bingham fluid. For otherwise, this tau y is not added for the other fluids. So if this tau y is added and then it behaves, this is parallel to this, we can say, and this is actually tau is equal to dou u by dou y to the power of n, with n is equal to 1, because this is linear curve. N can be greater than 1, n can be less than 1. So if we have the tau y initial stress is required to cause this, then that is a Bingham plastic. And if this n is less than 1, that means this viscosity increases, okay, with the rate of strain rate, then this is thixopetric, and otherwise it is called as the rheopectic materials. So these are the various types of the fluid. Like for example, if you take a toothpaste, for example, a toothpaste itself, it will not come. We have to press the toothpaste and then only it will start to flow. That means the initial tau y is required for the toothpaste to come out. So the tau y is the actually the tau y, it is the initial stress or the yield stress it is given, then only the toothpaste will come. Okay, so that is a very good example for this plastic fluids. Oh. So that's what this is a Bingham plastic material. This is actually should have been here, and these are actually the non-linear behavior of the. Oh, I had to remove this. How do I remove this? Where is the eraser? Okay, that is good. Sorry for that. So, so basically, actually, we have this Newtonian fluid, a non-Newtonian fluid, and this is the Bingham fluid, and there is another two class of the Bingham fluid that is that requires the initial shear stress for the flow to cause. For this Newtonian fluid, there is no initial stress that is required to cause the flow. So this knowledge of the fluid is very, very important in understanding the magnetorheological fluids. Simply put, these are also magnetorheological fluids, MR fluids in short are called. This is also a smart fluid. It is actually, it works in this area. The fluid with this will show the non-linear behavior, flow characteristics, MR fluid. Okay, so MR fluid is simply put, it contains so MR fluid is a smart material. It just contains some oil like a silicon oil or any other oil filled with magnetic particles. And if we observe this first figure, this is a fluid with the magnetic particles. The magnetic particles are shown in this as a spherical red dots here. And if we don't apply any magnetic field, they are not aligned in any direction, as shown in the figure A, without any magnetic field. If we apply this magnetic field, then all these magnetic particles will align under the effect of magnetic field, and then this flow becomes restricted. Or in other words, the flow properties of this fluid, which contains a very small amount of the ion particles, can be changed by applying external field. If magnetic field is applied, it is called magnetorheological fluid. If electrical field is applied, it is called electrorheological fluid. These are the two kinds of the rheological fluids that people commonly use. But most of the research are done on the magnetorheological fluid because it is very easy to control and also it is very easy to manufacture. So the magnetorheological fluids are the suspension of micro-sized magnetizable particles. Magnetizable particles, basically, we are using the ion particles because it is easy to magnetize in a carrier fluid, which is called a silicon usually. But we have done carrier fluid with many different types of oils at NIT. So that I will explain to you in the later slides. But magnetoelectrical fluids are just contains a fluid, basic fluid, and a particle, usually magnetizable particles. And when the electrical field or magnetic field is applied, then they will align, and therefore it changes the viscosity. If we change the viscosity, its property like viscosity, other properties changes, and if other property changes, that can be used for various applications. So basically, magnetoelectrical fluids are the fluids with the ion particles. So I don't know, keyboard is not working. Yeah. So as I explained earlier, the magnetoelectrical behaves like a linear viscoelastic material, or it is a non-linear behavior, and it is a non-Newtonian fluid. As shown in this figure, we have this tau b, that is yield stress, that is required to cause, and in the in the yield stress, the relation is tau into the complex modulus into the strain, that is less than the tau yield stress, and above this yield stress, this is tau b, that is yield stress, plus mu into shear rate, the shear strain rate, gamma dot. This is gamma dot, as the tau is greater than tau y. Simply put, it will have a two region. One is the pre-yield region and another is the post region. And here the shear stress equation is not simply mu into dou u by dou r, dou u by dou v, or dou u by whatever the dimension you take, the dou u y or x or var in cylindrical coordinate system. That is, here you have to take the mu into shear strain rate instead of the shear, just the shear rate. Okay, shear strain rate you have to take in this equation. That's all. This is tau y plus mu into, that is this rate. So there are three modes that are commonly used. One is called the wall mode, or called the flow mode. Another is called the squeeze mode. Another is the third one is the shear mode. So these are the three modes. People have developed several, brakes, clutches, etc. People have developed using these different types of mode. Here, the magnetic field, the flow and the magnetic field, if you see, they are in perpendicular direction. And the flow is in this direction, and the magnetic field is in the perpendicular direction. The pressure drop across the fluid as it flows through the device. Magnetic field is varied in the direction perpendicular to the flow. Just now I have told you that this is the flow direction and this is the magnetic field direction. Flow direction and the magnetic fields are perpendicular direction. Such a mode is called the flow mode. In the squeeze mode, what will happen? We have two plates. Magnetic field is applied. Of course, this magnetic field is also perpendicular to the flow direction only. Here, the force acting is actually, it is axial to the magnetic flux lines and the particle chain. Typically, in the squeeze mode devices, there is a little or no flow of MR fluid, and it is employed in controlling the small displacement vibration applications. The third is the shear mode, where the force is applied to the top plate, and the fluid just shears out, okay, as shown in the figure, and the magnetic field is perpendicular to the flow direction. In all these cases, the flow and magnetic fluid are perpendicular. Only this, where we apply the force, in this squeeze mode, the force is applied in this direction, motion is also in this direction, whereas here the force is applied into the plate, and this plate is stationary and this plate is moving, and this mode is called the shear mode. And if the force is perpendicular to the flow direction, that mode is called the squeeze mode, because it will squeeze this liquid. And if this is the flow and if there is no forces applied, then there is only a pressure drop, such a flow mode is called the flow mode. So these are all the three important modes of the MR fluids. And these are all the MR applications. Each one we will get into the more details in the slides to come. MR brakes, people have used these MR brakes. MR clutches, people have designed. People have used these MR fluids for the washing machines. People also developed a prosthetic leg. Korean researchers as used for the prosthetic legs and suspension of the vehicle, and even for tool vibration isolation in machining applications. It finds its place in many applications where either damping, vibration reduction, or application of the brake and clutches are concerned. Okay, so these are all the typical examples of the MR fluids, and since it is a mixture of the fluid and some carrier material, so it is called smart materials. So MR fluid, actually, what are the components of magnetorheological fluid? How do we produce these magnetic fluids? Magnetic fluids are available in the market by Lloyd's Corporation, but this is very expensive. It will be around 1 lakh rupees per 1 liter or even more. But these MR fluids are manufacturable. We also can make these MR fluids. We have made this kind of MR fluids in the lab. People are making this MR fluid. It is not a difficult task to make MR fluid. We need to have a magnetizable particles like carbonyl ion, electrolytic ion, water atomized ion, iron alloys, and low carbon steel particles. Usually these people, many people, researchers have used the electrolytic ion or carbonyl ion. So this, because these are available very easily, we have purchased this from the Pune vendors. Carbonyl ion, CI particles, CIP, it is called. CIP is commonly available in the Indian market. Silicon oil, all hydrocarbon oil, hydraulic oil, paraffin oil, all this carrier water is rarely used because its melting point is only 100. All these oils are synthetic oils and they are not biodegradable oils. Then some, we have made some mixtures using very little silicon oil and other biodegradable oil like coconut oil, other sunflower oil, castor oil. This is very easy to prepare. This MR fluid is very easy to prepare. And some additives are to be added like the flumed silica, gore gum, xanthan gum, lithium grease. These are all some of the additives that are added to the MR fluids to make this MR fluid more acceptable for different applications. Normally, we have used only grease in our experiments, and not all these kind of additives we have added. And it is not really necessary to add all these additives, but and all these oils and all these particles. Just one or two elements we can pick from this each, but I have presented all these common magnetizable particle, carrier fluids, and additives in this slide. We can make this particle, we can make this MR fluid easily in the lab using this ingredients which are readily available in the Indian market. After once, if you have made the MR fluid, if you are if it is purchased from the Lloyd's Corporation UK, it is no need to characterize. But if we make our own MR fluids, then we need to characterize the MR fluids. First is the preparation of the MR fluid. That it is discussed anywhere. It is discussed in most of the papers that it is not a difficult thing. So there is a set of procedure to prepare the MR fluid. You have to stir it for certain hours. And you have to mix it. That simple procedure, lab procedures. So that preparation is easier. After preparation, we have to synthesize. After synthesizing this MR fluid in the lab, we need to characterize this fluid. Like, for example, the particle distribution. Okay, using the particle size analyzer as shown in this figure, particle sizes versus the frequency is plotted here, and usually 10 to 15 micron particle size is usually used in the MR fluids. We have also used around the 40 to 50, that whatever the supplier is claiming 40 to 50, you can easily see that this distribution, if he's claiming 10 microns, so the distribution will be around like this, 8 to some say it is around 40 microns, is in center around 50 microns it is. So but 50 is where number of particles with the 50 microns is less, it is mostly around 10 to 20 micron size particles. So this is a particle test we have to do. This is the first test, and we have to do this the SEM then to see really that how this distribution of the CIP particle. You can see this in the liquid. The particles are very nicely there, and then there's size also. You can see that is very nice. It is here. Okay, and after that, one of the property is the magnetic property, magnetic moment versus that is for the magnetic field strength. That is in the vibrating sample magnetometer or VSM. We don't have VSM at NIT Calicut, but IIT Madras is having this vibrating sample magnetometer. So this is, as I told you, we have used CIP particle, carbonized ion particles. So we can do this kind of a test using this vibrating sample magnetometer or VSM for, and it is clear that it is for these larger particles, the range for this magnet moment is smaller. All these are very important. We'll see one by one, and we have to find out the temperature stability of the particles that we use for different applications like brake applications, etc., and TGV to see what temperature it will drops its property like weight, etc. That also study people have done, and we have this stirrer and the rheometer in NIT Calicut, and that will cost around it is a rheometer with the magnetic setup, and the magnet, this is a rheometer I'm showing. This is a rheometer with the antenna bar. We have at NIT Calicut. This is the NIT Surathkal also is having that this rheometer, and this whatever that MRD cell, that cell it is around 4 lakhs rupees we have recently purchased, and this is an add-on onto the rheometer. So that so this is how we characterize the MR fluid. First we synthesize the MR fluid in the lab. It is very easy. It is just you put this ion particle, silicon oil or whatever that oil compatible with the silicon oil, means not any oil we can put. We should be compatible, like in terms of the viscosity, temperature, all this has to be compatible with the silicon oil, because most of the industries are using the silicon oil, and if you have to substitute certain oil, and that oil should have a same or near properties as that of the silicon. That we have to keep it in the mind while preparing the MR fluid. And these are all the properties that I already explained to characterize the MR fluid. So this is the first step, preparation and characterization. And this is, I already told you that this is a Herschel-Berkeley model is commonly used to model the MR fluid, because tau is equal to initial yield stress is required into mu, that is from the Newton's viscosity, into the strain rate, and the P is index like earlier I have shown in terms of N. Here it is replaced by the P. That P is called, or N in that first slide is called the flow behavior index, and N is equal to 1 for the non-Newtonian fluids, and tau 0 is equal to 0, and then it will become a Newton's law of viscosity. So here this is the graph that is taken from the rheometer that will draw the shear rate. This is shear rate versus the shear stress. So this, if you see this one for various oils here, for under the various VSM, it shows a different behavior. It means it is having the initial stresses. For example, if it is 95.16 kiloampere per meter, if this is the field that is applied, then that yield strength is more here, around say 150 or 180 kilopascal. If you reduce that to say 53.8, then it will be around say 100, around 100. And if this is the red one, that is around 30, this will be around 25 to 30. So that yield strength is actually a function of the field that is applied. And this is the shear rate that is drawn on the x-axis. So these kind of in any research paper, all this is whenever they synthesize their their one fluid, this type of graphs are available in the research paper. Of course, if you are buying from the standard supplier, and this they will give it to us. So let us move on to the next characterization. Effect of temperature, as I've already told, this effect of temperature versus the sedimentation. This is a very important property, because as soon as we put these particles in the magnetizable particles in the fluid, these particles actually has to mix very well with the silicone oil or whatever that oil, okay, we use, and that after some time, these iron particles are heavier usually compared to this, and this will come down. So this and it will come down and it will stay. So this should not happen. So how much it will sediment, how much it will after 1 day, 2 day, 3 day, 4 days, how much of this particle will come and settle down is denoted by the sedimentation ratio. And this is the reason why we add additives, various additives we add to prevent this, the sedimentation ratio. That is, if this is the fluid is well mixed, well prepared, then it will settle after a long time. Otherwise, if it is a very not nicely prepared, then it will sediment at a very faster rate. So sedimentation is really a problem. One of the problem we have also faced, and the sedimentation rate we have drawn here for various temperature, and also various times, say 100 hours, 150 hours, how much it is going to sediment and sediment for a given time, say after 1 hour, 1 day, 2 days, like that. We have drawn it for a number of days also, that I'm not showing here. Similarly, these are all some of the graphs that is as a function of temperature we have drawn for the viscosity versus the shear rate. That's the viscosity curve. Shear stress I have already explained, shear stress versus the shear rate for various currents. If you see this current, if you increase it current, okay, then that shear rate also will increase. So if you see it, for example, it is 80 degrees centigrade, zero current, and okay, and if this is 80 degrees centigrade, if this is 30 degrees centigrade and 2 ampere, so it will be this curve. Okay, so from this you can see this, the yield strength of this 30 degrees centigrade 0 amperes, that is 30 degree 2 amperes, it is here. Here red one, and if you see the 30 degree 0 ampere, which is here, so you see this is 0, almost 0, and this is having a very high value of the shear stress. That means by applying the magnetic field we can vary this shear stress. So that makes it very interesting property. So there are sedimentation study done on this MRF oils, different oils, hydraulic silicone oil with 30 CST and hydraulic oil with 40 CST centistokes. So like this sedimentation study can be carried out, and we can study the time taken for sedimentation at different temperature. This study we have to do once if we synthesize our own product. This itself can be a very good study, mixing different oil and study their behavior. This itself can be a very good research topic. So now we will get into one of these applications. We have now visited how to prepare this MR fluid with these 3 ingredients. One is the basic magnetizable particle, and another is the basic fluid, like a silicone oil or any other oil which is compatible with the silicone, which is having a similar property with the silicone oil, and the additives. This is how mixing this in a proper way gives us the MR fluid. And it is really simple to make this MR fluid. After making the MR fluid, and a few tests are conducted. Basically, these are rheological tests, and like shear stress versus the shear rate, all these tests, and the temperature dependent properties of our shear stress, and these are all available. Temperature can be increased in the rheometer and can be studied. No separate experimental setup is needed. All this can be can be done in the rheometer, and of course the sedimentation rate can be found out by simply observing how much the level of the test tube is going after 1 day, 2 days, and you can determine the sedimentation rates. This is how we characterize this is how we characterize the MR fluids in our laboratory. Now this we will discuss one of the many applications are there. We will discuss one of this application is the MR brake. How this MR fluid can be designed as a brake. This is the first question that I would like to answer. The brake means the wheel is rotating and we have to stop the wheel. So that means we have to apply the force to stop the vehicle, to stop the wheel. And if we have, for example, if we have a disc which is rotating, and if we have another stator, stator which is stationary, and in between, if I put the fluid, and if I magnetize that fluid, then it will act as a solid particle, solid part, and a brake is applied. If I remove the magnetic field or the current, it becomes the fluid and brake is released. So it is a very simple technology. MR fluid is a simple technology. If we apply the brake, it is like this. It is a basic principle only. Many of you may be knowing it. It is a basic principle only. Like I have the rotating member here, one member, and I have a fluid here. And if I apply the if I don't apply the magnetic field, it will be something like this. And if I apply the magnetic field, and these iron particles will become a solid, and there will be a brake that is applied between the rotor, that the wheel, and the stator. So if the rotor and the stator is filled with the magnetic fluid, and if this field is applied, and if this becomes solid and these two will not move, then that is brake is applied. Or if I apply the magnetic field, and if these are free to move, and if this moves and this also moves as an integral part. Please hold on. Sorry. So that is how the brake can be used. That is how the brake can be used. So we have the rotor. Rotor means the rotating part. Stator means stationary part. In between, you apply the magnetic fluid. And if you apply a magnetorheological fluid, and if the current is supplied between the current is supplied to the magnetorheological fluid, and it becomes a solid, and brake is applied between the rotor and the stator, and the rotor will stop. And here, many people, this is one of the exercises we have done for the commercial vehicle. What is the braking torque that is available on the front wheel with the pylon rider with this dimension? Then we have found that braking torque on the front wheel to the rear wheel is around 4.4. Whereas if you have another pylon rider, then all these CG etc. will change, and the torque will actually increase on the front wheel, and the torque on the rear wheel also will increase. But the ratio will be around 3.5. So if we have consider with the rider alone and with the pylon rider, what will be our braking torque that is required to brake this vehicle? So this is a variable, variable weight or variable rider, 1 rider, 2 rider, 3 rider. Based on that, we can actually calculate the braking torque, and for that braking torque, we can design the braking MR brakes. That is the idea we have started with for 1 pylon rider and the 2 pylon lidars. So CAD model we have done for the MR brake, and we have done this mathematical modeling using the console software that is available in NIT Calicut. And we have actually derived this equation. This is the actually the schematic that is showing the tire. And we have removed this actually the disc brake, and we have fitted our own MR brakes. And we have done this kind of analysis using the console, and we have derived this torque equation. And from here it is can be seen that it is R0 cube minus Ri cube. That means it is torque. If I increase this radius, then the lot of torque can be generated, or lot of torque can be brake using the MR fluid. So this is the equation, and this can be actually simulated. Here, this is a rotor, and whatever that is shown is actually the material, and this is the stator. And when this magnetic field is applied, this rotor will catch this. The rotor will come to the rest, because this becomes the solid. So that is the idea in the MR brakes. So MR brakes basically consisting of the rotor and a magnetic magnetological fluid and some arrangement to have a winding, and which the windings are connected to external agency, and if current is supplied, then this becomes a solid and the brake is applied. So this is not a very recent technology. This technology is there for many years, but we have done it for the commercial vehicle. So let us move on to the next slide. So this is the CAD model my students have developed. Initially, we thought of developing using this brake pedal assembly that is available commercially with the motor. Then finally, we have fitted the engine and we have tested it. So this is how it looks. That experimental setup looks like this. You will see the actual one. In addition to that, actually, we have also developed the model in the console, and my own students have developed a software to create this kind of a material, this kind of a diagram. If you give the MR fluid and properties and all, this will give me the the flux density, etc. This kind of a software my students have developed. Actually, UG students have developed. So here, this is a disc, that is a rotating disc, and MR fluid is here. I'm showing that figure number 4. I hope you are all seeing this figure. MR fluid is there here, and disc is there. And disc I have to stop because this disc is mounted onto the wheel. This disc is mounted onto the wheel, and this disc has to be stopped. That wheel has to be stopped. There is a MR fluid, and this is the housing. And housing is fitted to the chassis of the two-wheeler, and I have a coil. I put the magnetic field, and this becomes the solid, and the disc is prevented from rotation. That is how the brake is applied. These are all the dimensions that corresponds to that design, and we are using that equation that I have shown. If these all dimensions are put, we can get the theoretical torque capacity. So this is very clearly shown here. One coil here, disc here, and MR fluid here, housing, and this is how it looks. So this is how we have used this Berkeley model. I have already told that this is a non-Newtonian fluid, and this equation we have used, and we have modeled this mathematically using the Berkeley model to predict the MRF behavior under high shear rate condition, that is non-linear behavior condition. And then this section 1, section 2, section 3, based on that we have calculated the total torque, and we have added the torque. That is, these 3 components are added for this section 1, section 2, and section 3. So y is equal to this. This we can express actually the rheological property as a function of the magnetic density that we have calculated like this, and the yield stress we have expressed in this form. And n, this is not very important. This is simply a mathematical modeling we have done. The flow index behavior we have expressed, and consistency index k we have expressed. And we have arrived at these constants experimentally. So the MR fluid MRF 132 DG, this we have taken, okay, this we have taken from the Lloyd's Corporation, and just for modeling purpose we have done, and we have calculated. Just for modeling sake we have calculated, because all these constants are not available to us, so we just use their constant to see whether our software is working, our modeling is working properly. We also modeled using the Hershey-Berkeley model. So the equation that is just now earlier I have shown for the section 1, section 2 and the middle section. So using the Hershey-Berkeley model, we have obtained the braking torque around 214.75 Newton. This is really a very high torque. You may be knowing that the Hero Honda, whatever we are using in our day-to-day life, it is around 10 Newton meter. And this torque, what we can generate is really a high torque. Okay, so that means our design, theoretically at least it will satisfy, it will be able to develop. And this is only a theoretical, therefore our simulation study is required to support this our claim. So we did the simulation. So from this graph provided from this MRF also we have put our property, our fluid, we have got 214, and using that the Lloyd Corporation from UK, we have used this 132 DG property, and then braking torque we have got it as something near to them. So we have plotted this flux density versus the flux field strength using the MR 32 DJ, because this was available, and for the magnetic silicon steel that we have selected, for that also we have drawn the magnetic the steel, the parts are made up, the rotor is made up of the magnetic silicon steel, because that flux should not leak and flux should reach. For example, here the flux, here coil is there, the flux should come here and it should come here till here, then only this whole disc is prevented from stopping. Otherwise, if this flux density is only here, then this place the brake is not applied. So this permeability of the disc must be good. That means it should allow this magnetic field to flow through it. Therefore, we have used this silicon steel. Okay, silicon steel material is used to have the good magnetic flux density. Okay, so coil is copper, magnetic core is silicon steel, and MRF 132 DJ we have used initially for this simulation purpose. Later on, we have not used this MR 132 DJ. We have done our own fluid and bobbin, etc., where we have to mount this copper coil. That is all non-magnetic material we have used. We have used aluminum for that. So that entire thing, 2D drawing is shown here. This is done by my students only, all this work. So they have parameter, this parameter they have taken for various combination of the parameters. All these parameters they have actually optimized. This one, they have optimized the disc thickness for the clearances, for various clearances, for various disc thicknesses, for various clearances versus the clearances in the section 1, 2, like earlier I have explained. This kind of a study we have done using the COMSOL, and we have found out that what is the effect of clearance, that is the clearance for the MRF, how much clearance we have, how much material to be filled, right? How much MR fluid to be filled. What is the effect of that clearance? That we have studied in great detail, and disc thickness we have kept constant, and we have varied that clearance, and we have found that for certain value we are getting 330, 254, etc. Some clearances are very difficult to manufacture, but we have done all this, to study to see what is the effect of the clearance. And the noteworthy change in the braking torque, we have found out that the braking torque is actually a function of the clearance. So optimal clearance is very much important. In the section 2, okay, the change in the clearance gap does not affect the braking torque. That is what we have found out, where we need to change the clearance, where we have not to change the clearance. Okay, no appreciable variation. If you change the disc thickness, there is not much variation, because 271, 270, it's almost clear. But if you change the clearance, it will have a good effect. So clearance obviously has a important role to play, obviously, because and people we have also studied, my students also studied with one coil. Okay, if you make only one coil like this, what will be the effect? If I make divide into two coils, what will be my effect? What will be three coils? Such a kind of a study we have made, and we have passed 1 ampere current, and this is 24 wires we have used and did this simulation work, because this kind of a the winding difficult to do and test it. So we have done it with the console that is already available in the market. So already available in our NIT. So it is can be seen that it is a single coil for all. The very important thing is that we have not changed the total power consumption. We have kept this. In fact, one of the reviewer in our paper, earlier we have did it for different power. Then they were asking us how you can compare this magnetic flux density with different power. Then we did this simulation again by keeping this power constant and see the average flux density. And it is obvious that we should go for the single coil setup because it gives the good 0.31 Tesla. That is a magnetic flux density in the MR region. So this is very clear from this single coil. Okay, this single coil can give a good flux density can compare to the 2 coil, 3 coil. This kind of a work can be done. It is not a very difficult. And we have also done this coil width and coil height, and we have find out what kind of coil height, coil width, etc. should be studied and used. So after doing this, one is the synthesize the magnetic fluid, and then you characterize the magnetic field. And then after doing this, once you did the design, we need to calculate or we need to simulate what are the effect of this coil dimension, this dimension, and height. All this, each one can be taken as one single problem and can be done. This variation of the coil width, the coil height, etc. we have done, and we have selected this optimum design based on our findings. So this is actually the number of turns, coil wound, coil height, width, etc. By changing this one, what is this variation? You can see that variation is not really much. It is varying from 213, 213, 218 maximum around there. So this width and all this will not matter, but number of coils matters a lot. So that is what we can say from this study. We have learned what is the effect of coil wound height, coil width, and wire diameter. So this student also studied the taper angle of this disc, whether taper angle will have an effect for 0 degrees, like that. For weight reduction, my student has done for Karthik Peri, and he has found out the various, for taper angle 2 degree, 4 degree, 2 degree, 3 degree, 4 degree, what will be the flux density. All those things we have done. We have also done, okay, this is the fluid and the magnetic field is there. Under the magnetic field, how that fluid will behave, that is a very important. Okay, so that is expressed by sigma is equal to the yield stress, that is around 12.8 plus this 0.098 and shear rate. So that is that's how we get the that's how it is we get this graph from this CFD analysis. So as I told, the magnetic analyzer, my student has developed from using the front end of the console, and he has developed this for a software. And if you give this dimension, it will give the complete magnetic. Available function is to geometry, coil parameter we can give, properties. That is how we have given 132 DG properties. Meshing parameters we get, and if you set the solver, it will generate the report on its own. So this is what we have developed. Okay. So after all this analysis and calculation, we have actually fabricated this at NIT Calicut, and this is a IC engine that is connected to this flywheel, and then to this wheel, the two-wheeler, and this is a brake. And in fact, this much brake And actually, when we design, we have designed it for 210 Newton meter. This much Newton 10 meter, even it is good for four-wheeler, because as I earlier informed to you, audience, that the Hero Honda requires hardly 15 Newton meter, whereas our simulation can actually generate 215 Newton meter. That is why this disc is very big. In fact, if it is only for 15 Newton meter, actually the size will reduce very drastically for our Hero Honda vehicle. We have done it for Hero Honda vehicle here. This is one of the this one we have done, and we have this is 2 years back work we have done, and this got also the innovation project fund from NIT and elsewhere. And MR brake assembly we have done, of course, and then there was some problem. We have identified that seal problem, and now we are also working on that problem, seal problem, to rectify that design. So this is earlier we are not having this torque sensor, because torque sensor was actually cost around 1.5 lakhs. Now we have purchased, and now we are planning to replace this one. And in fact, we have removed this one and we have replaced this with the motor and the torque sensor. So motor is a better option for constant speed experiments. So we removed this, and since we have the torque sensor now, we have made a different assembly. So this assembly, as I earlier was telling, this directly motor is connected to the flywheel, then to the torque and the brake. That is how we are going to test this in this year. So this is a new rig we are going to fabricate. This is the first kind of this is the brake, one of the application of the MR fluid. The second application what we have developed is actually the based on the braking system. MR fluid can actually stop the rotating disc by fact that whenever the field is applied, it becomes solid and the brake is applied. This is in very fraction of a second. Mechanical brakes take some time, but in the MR brakes you can apply in a fraction of a second, microsecond. Second project we have done is dynamic vibration absorber. This also we have done. Usually, vibration are everywhere, and vibrations are to be reduced in many applications. So we have designed a vibration absorber using the MR fluid. These vibration absorbers are there. Vibration absorbers are there in people have done, many IIT people, other people have done these absorbers. These are common absorbers, but what we are doing, this absorber is a semi-active absorber where this damping coefficient can be changed. Here, once you, for example, if you use this Hero Honda or any other vehicle, Bajaj or any other vehicle, we have a shock absorber, and that shock absorber is filled with the oil, and that oil viscosity is constant. SAE 30 oil, SAE 40 oil, that we go to go to the petrol pump and we fill that oil, or during the manufacturing they will fill this SAE 30 or SAE 40 oil. That once you fill that oil in your shock absorber in the two-wheeler, that is not going to change. That means the damping coefficient is not going to change. But here, if I change the viscosity, I can change the damping coefficient or damping characteristics. That is the beauty of the magnetorheological fluid. By changing these damping characteristics, I can control the vibration, because actually vibration can be controlled by controlling the damping factor. And the spring, or when you have a damper, its stiffness also can be controlled. Okay, so this becomes something like a semi-active control. So we have used this semi-active control to design dynamic vibration absorber for the primary mass. So what we have done is actually our objective was to completely optimize, design DVA, optimize this one, and to do this stability analysis and gather the experimental data to see what is done, what is going on in the vibration setup. This is also done by my students, Ganga Nair. Now she's in foreign university. She got into a very good foreign university. She's also a very high CGPA student, and this is the thing we have done for developing that MR based DVA. So here, this is the machine, and this is the isolator, and this is the rigid base, and this is the observer, dynamic observer. This is the mass, secondary mass that is used to absorb the vibration of the machines. So this here, if you see, these are the standard dynamic observer, which will have a M2 mass with the C2 as the damping coefficient for this damper, which is not variable, and the spring. So if we can write the expression for this M1 and this M2, this equation will be like this. And combining this, this equation can be rewritten in form of K1, K2, because this K1, this is nothing but K. Okay, this is nothing but K by 2, K by 2. This is parallel, so we can add in the springs, that is nothing but K. And we can write in terms of the x1 dot, that's acceleration, or x2 dot in this way. So if we use this very famous bow when hysteresis model, we can show that y dot, this y dot, the velocity is, can be shown like this, and z dot, that can be shown like this, and damping force is equal to C1y plus K. This is a mathematical model. Don't have to be too much worried. We have modified this when model, and we have wrote this just a velocity equation, the y and z. That's all we have done, and this is the force, that is damping force. So we have defined this alpha C1 C naught, and then we have done using Simulink that is available in the MATLAB. We have inputted this 1, 2, 3, 4, 5, like this equation. Okay, all this equation we have modeled using this model using the Simulink, and then we have solved this equation, and for various displacement we have drawn the force. I will show you the experimental results also. These are all the standard simulation value versus the displacement versus the force. And this you can see that these are all the from the literature, and see how closely this is also matching. This behavior and this simulation behavior is really not, at least the behavior is it is 0.03, 0.02, and 0.015. At least this area, this is quite clear that this our experimental value done somewhere else by some people, and actually the behavior looks very similar. Obviously these oils are different, but their behavior, if you see our simulation and their actual experimental work, actually closely matches. So this is how that displacement versus the time that is drawn, and displacement of the primary mass, and this is the force exerted by the dVA. So this is static magnetic analysis, the flow analysis. Okay, all this analysis we have done. Basically, earlier I have explained how to do the magnetic analysis. Means various parameters we change and see whether this magnetic flux density we get, and whether the proper flow is there. That only we are doing it here. Only magnetic flow analysis using the COMSOL, and flow analysis also in the COMSOL or in software like ANSYS. We can do it and bring it here. And after studying this fluid, and then we have designed this the damper, which is a twin tube double-ended damper. So people, we have tried MRF 132 CG for simulation purpose. Solid content is 85% by weight, and yield stress we are getting around 59. These are all the values of these options. For various options, we have calculated all these values, and we have selected this MRF 132 CG for this because the yield strength is 59 kPa. So then using that fluid, we have simulated the magnetic analysis for materials 1, 2, 3, and 4. 1, 2, 3 is a piston here, and then 4 is a coil. This is 4 is a coil. 4 is a coil here. 1 is a material. This is a piston. Okay, iron. Okay, 2 is also a piston, part of the piston. Okay, and this is okay. This is 4 is a coil. Okay, then 5 and 6 are the cylinder walls. This is a piston. This is a cylinder wall, and this is the fluid. The number of turns vary, and magnetic flux density, current we have changed, and what is the flux density we are getting. That kind of a study we have made, and BH curve for MS, so MRF 142G we have done, and because all these properties are available, so we took MRF CG, and then we have did this simulation, because COMSOL asks various properties, and some of these properties we cannot do it here because of the cost. And even though we have made this fluid, we could not do so many tests because of non-availability. So using this fluid, standard fluid, we have analyzed all this, and in case if we get some funding, we will buy and do this experimental and compare the simulation that. So these are all the fluid analysis that we have carried out, and then we have studied how is that flow, viscosity versus the magnetic plot, all these things. Basically, how that viscosity will change versus when I increase the magnetic flux or magnetic current, that is of very importance, and whether my field will reach till what distance, that is also very important, and how that fluid property will affect that my magnetic field, that is also very, very important. That is how we studied various options using the COMSOL, and we have proposed the Bingham-Papanshu model. I am having difficulty to read this name. So this model is proposed for this MR damper. We have used this model, and we have further developed some of the equations, and we have solved the equations, and we have done the simulation for all these currents, and obviously the load increases with the current increases, load carrying capacity also, piston on the or the damping force also increases. So this grid independent test, when we do the meshing, we should do grid, because we cannot use a very, very fine mesh. Till what mesh that that our results are accurate, that actually grid independent test I told them to do, they have done this, and they have found out up till what mesh is okay for simulation work. This is the setup that we have made. So this is the lab setup done by our student for this MR damper, this auxiliary spring, and then this primary mass vibration, primary spring, primary mass, and primary spring. This is the primary machine one. This is the same thing. Primary spring is K1 by K2, K by 2, this is K1. And you give the excitation by the motor and the cam. This will start to vibrate, and it will violently vibrate. And then you, by changing the current to the MR fluid, and by changing the K, and by changing the C2 of this MR fluid, this moment can be controlled. That is the vibration of this machine. You can incorporate a machine here, but we are experimentally showing that this is the primary mass which is vibrating violently, and that can be reduced using the MR damper. So that is what we have done. This is also a funded project. So my student also have proposed some self-powered magnetorheological harvester that we have not done. Actually, this is suggested as a future this one in their thesis. So these are all some of the innovative things they have suggested for the future, and I actually request all the participants, those who are interested, to actually make collaboration with us, and so that we can make other products useful to the society or automobile, and that students can come and do the work in the NIT, and we can combinedly do the work even in the MTech level, BTech level, PhD level. This work can be done, and you can take also the credit of your work. So MR clutch, currently this work I have given it to one of the students, few of the student, that this currently we are, Hero Honda is having the Hero Honda. I will show this setup. This Hero Honda is having the wet clutch here. This is the transmission system. This is the crankshaft, and this is actually the flywheel. This is the gear wheel. This is the actual drawing my students have made this existing Hero Honda wet clutch, and our objective is actually to replace this wet clutch by the MR clutch. So this is the arrangement we have made. So we are going to replace this. We have already made this kind of a design, and we are going to replace this wet clutch by our MR clutch. This is work is underway, and is also going to be patented. And this is the setup we are going to build. We are not built this RPM controller, this servo motor, and torque sensor, and then this is a hub model. This is what we are going to do in this semester. This work is on the MR clutch. So materials etc. are selected for this, and this has to be fabricated, and we have got some funding for this work also. And students have done this kind of simulation work, and some optimization algorithm for stimulated annealing or quadratic programming algorithms are used for simulation purpose. Another work, interesting work we are taken. This work is variable wall technology using the MR for engines. This is the model that we are that is shown in the figure number 1. This is a Honda engine. This is a conventional wall technology. All of you know there is an inlet valve, there is an exit valve, there is a spring control valve, and there is a camshaft, and this camshaft is connected to the crankshaft. So here, nowadays I will show you that. So here, the earlier when I was in SJEC, actually professor has tried these solenoid valves. Okay, but solenoid valves response is very, very high. That's why we could not use open and close using the solenoid valve. Why we were in the SJC only, we tried this valve, this concept. Then later on, when I came to NIT, then I thought of using MR fluids in this assembly. So we are in a process of developing this the conventional valve technology with just only the spring with the MR fluid technology. This also got a funding from the director of NIT. There is 3 technologies that you already know. Continuously variable wall timing, CVVT in your cars and all, you can see this, or CVVL, continuously variable wall lift, where you change this lift, because the lift etc. are very important to control this the blow by, and also the fluid, whatever petrol mixture or diesel mixture should not escape during the valve overlap. So that is very, very important. And in the CVVD, continuously variable valve duration. So these are the technology to vary this valve lift timing to get the optimum combustion effectively. So these people are using this, all the car manufacturers are using this technology. And now where are we doing our work here is that here in the MR fluid, this is a magnification ratio versus the frequency ratio. This graph we have drawn here. For R, the zeta value is equal to 0.4, zeta value is equal to 0.2, 0.1. If you change this, the damping ratio, zeta, usually zeta in this graph it is R, damping ratio, then your magnification ratio will change. But this is for one oil. As I told you, in two-wheeler, if I use SAE or if I use some SAE 30 oil in our Hero Honda or Bajaj or somewhere, okay, then this damping is fixed. It is not going to change. That because we are not changing the oil once we buy the bike for the suspension system. We are changing the engine oil, but not the suspension oil. So this R is fixed. That means this graph only we are operating. But in the MR fluid, by changing the MR, by changing the magnetic field, I can get various R. So I can work in this low, I can bring this vibration to this much low, or if I want more vibration, I can go up to this vibration. So this variable damping ratio is possible using the MR technology. That is the really a good advantage of the MR fluid. So what is that we have done is that we have this, we have suggested this, this here we have this cam, we have the rocker arm, we have the upper spring and the piston, and this is the valve. Okay, now what we are proposing, I'll show you the final. This is a hand sketch way. This one, I will show the final design. Here, what we are proposing is this. This is a 3D model, simple model we have generated, but we have not fabricated. Here we give this along the spring that is available in the market. We are also planning to give the magnetorheological damper so that the damping, opening, closing, etc. can be controlled. So this is one design. This is another design. Like this, we have come up with the various design to for this engine, which is having only this kind of a suspension system. Only this kind of a suspension system it is having. It is not having any damper here. So we want to introduce a damper, and that damper should, it is not one-time damper. It should be a dynamic damper, like a magnetic damper. That is our idea of using the damper there, magnetic damper there in the wall variable wall technology cars. So that is effectively what we have done. But that is what we have suggested. These are all we have covered already. Ashley-Berkeley model, Bingham model, and all. The same thing we have modeled using the Ashley-Berkeley model. The same thing, and we have used, and same process is repeated here for selection of the fluid and mathematical modeling. Same earlier we have done, and control strategy has to be developed for controlling, because this is an engine. Real-time control is required, so control strategy has to be developed for this engine. So how this MR fluid helps here, that you see inlet valve opens and inlet valve closes. This is the wall time diagram, and the 1 to 2 suction will take place. That means inlet valve will close after some time after the BDC, and inlet valve then 2 to 3 is the compression. Actually, this compression takes place much earlier before the TDC is reached. And then this is the power stroke. This is only one stroke during which the power is generated, and the inlet valve opens here, and exhaust valve opens here, and exhaust valve closes after some time. That means the inlet valve opening here, that means the inlet valve is opening before TDC. That means the petrol mixture or the diesel will come inside, and this exhaust valve is opening after TDC. I think you got it. So inlet valve is opening before the TDC, and exhaust valve closes after TDC. That means inlet valve and exhaust valve, okay, inlet valve and exhaust valve open during this time. So this is a very important, because the inlet valve is open means because petrol mixture is coming in the petrol car, and exhaust valve is also closing after TDC, and this all the petrol mixture or diesel mixture is going out. This is called the valve overlap. Overlap is done for a specific reason, and how do we control this reason is not possible, not effectively possible in the case of the conventional design. If we use, and this is going to be a one diagram for one speed, and this changes because this timing is all timing. If the speed changes, this timing also changes, and that means this changes. So this is not a static diagram, rather this is a dynamic diagram. Inlet valve may be here, inlet valve exhaust may be here, it may be here. So this has to be changed according to our need. Therefore, a controller and a MRF-based valve technology is proposed. Okay, and that is in the design is and patent is underway for this. That is what we have done. That magnetic field analysis for the permeability mu and mu3. All these relative permeability students have done this analysis for a different number of coils and different current, and they have optimized what kind of the viscosity, what kind of a range we should select for this four-wheeler. So we have not purchased that engine yet, and we have done some kind of analysis using the diesel RK because students are interested to do work on the diesel engine. So some combustion studies, etc., has been done. Cylinder pressure, mass blow, all those things are done, and now we are in a position to select this kind of an engine and some experiment setup to create. This is one currently we are developing this MR based wall time diagram, and this is another torsional damper. This is actually a patent that is not done by us, and this patent is no more valid. Here, people also, I am just showing for the benefit of the audience, August audience, so that they can also work. And these are all very, very complicated. And this, damper assembly is connected by means of a bolt, and then these are all, silicon balls. This is 1945. Silicon balls are actually used to dampen out the vibration of the crankshaft. But here, MR fluid can be used to dampen out this. You can fill the oil and you can put the coil here, and you can change, and you can change this torsional damper. This kind of a work actually can be done even at the UG level. The small engine can be purchased, and this crankshaft you can make a slot and make this coil and put the oil and steady this kind of a damping effect. That is just a kind of a work we can do. So these are all the work we have done. We have also designed this MR magnetoelectrical damper, that is a twin tube damper. This is single tube damper, and monotube damper, monotube MR damper. That means there is no passage for this oil to go in this twin tube. As soon as it presses, it will passes through this orifice and goes back and fills from the other side. This is twin tube MR damper, and this is the twin tube damper we have also developed, and this is a twin tube single tube damper. Actually, we have developed this twin tube MR damper long back. Now, so this is the setup. Commercial MR damper from the Lad Corporation was experimentally tested, and of course, okay, this is the hydraulic power pack to give this for this one. Okay, now servo controller to move this actuator. Hydraulic power pack, like a hydraulic cylinder, it will move, and then we have the damper, because the damper has to be given a linear motion. So this is linear motion is given by the cylinder, and the cylinder is operated by means of a hydraulic power pack. This will send this hydraulic power pack will contains the motor and the pump. When the motor is on, the pump will pump the oil, and the piston will move, and it will also move the MR damper. And we supply this DC power supply for this MR damper, and this is the oil that is used, and then this data acquisition system is used actually to capture this behavior. So that is the setup actually. Usually this basically this has to be given flow and motion, and for various current how this is behaving, that has to be as simple as that. And of course, different MR fluid oil can be used. This is actually setup. This setup is available in not at NIT Calicut. This is available with Professor Hemant Kumar sir, and this is just hydraulic press. We can also you can also try. There is nothing difficulty here. Frame and the hydraulic actuator. This is hydraulic actuator. This can be connected to the hydraulic power pack. This is given the motion. This is the damper, and this is the upper portion. This is load cell actually. Load cell probably. Okay, we have used the load cell in our setup. It does not look like a load cell here. It just looks like a clamp here. I do not know. Maybe a load cell. May not be a load cell also. Maybe they are keep capturing the data by the other this one. Okay, other means. But what we have done is that we have done this setup, and we have not used this kind of a expensive actuator. We have just used this vertical servo air motors itself we have used, and instead of this actuator, hydraulic actuator, we have used this air pump, linear pump, air pump operated by the air. We have used this linear, that linear pump will move this damper, and then we have used this load cell and we have captured that load, and we have measured the displacement. That is how we have measured. Here they have all this facility because they have funding from the heavy duty heavy machinery, that is 3 crores rupees project they have, Professor Hemant Kumar. So they have made this beautiful setup. So similar graph I have shown this one. We have got it simulated. This one you see how nicely they have got experimentally. So we have also got this kind of a graph. Actually, that results I have not shown it here, and we have also used the same kind of a model. This kind of a model we have modeled it, and similar graph experimentally also we have done that. Result I have not shown. Maybe there in the coming slides, and they have drawn this maximum force versus the amplitude. From here we can see how much force, the displacement, it will give. The force variation is lesser here in kilonewton, and the displacement range is, if you keep this displacement range, and these forces are more, and that is how this variation of the forces can be obtained, damping force, and thereby the vibration isolation or absorption can be done by controlling this the forces. Now, controlling the forces is by controlling the field. So this is what they have done for 0 ampere, 5 ampere, 1 ampere, and similarly by doing this one, we can actually draw the graph of the force versus the forces the time and the forces as the displacement. That is done by them. That is one of them I am showing because we have some collaborative work with Professor Hemant Kumar. Hemant Kumar is also one of the leading researcher in the MR fluid. This type of twin tube magnetic damper we have developed actually. That diagram, this actually we have also developed this one. They are showing this suctional view CAD model. We have developed this kind of a twin tube damper, and we have tested actually. And I think they have taken this damper from this company from Chennai and modified and filled that damper with the MR fluid. That is also possible, but we have actually manufactured this two tin at NIT a long back. This is the thing they have purchased and filled this, and they have filled this. They have made this setup. It's very similar. You provide this vertical motion to this damper, and study this various the parameters like velocity, force, displacement, etc. Here I will explain. This is the piston, and this is piston rod. This is connected to here, and this is screwed here, and over that this coil is put. That will be the over that there is a cover and the top plate. Top plate. This entire assembly is covered with the top plate, and so this oil will not go, and then this bottom plate to cover this, and after that it looks like the whole thing is put inside the twin tube. This is a twin tube. This twin tube they purchased from there, and this they have made and put this MR tube. Probably they have used this. I do not know. They have probably used this one. And we have also made this kind of thing, and we have also tried how to, if we give this different geometry and taper angle, what is going to be our magnetic effect. That we have tried, and we have shown that instead of this straight, actually the tapered, if you make some tapered angle, this will have a better performance. We have shown that, and we have published that result. These are all the result I have already explained. These are all the common graphs we get from the damper for various current and velocities. Velocity can be controlled using this hydraulic power pack. Q is equal to A into V. By controlling the flow, we can control the velocity of the actuator. Velocity of the actuator, if you can control this, the moment of the stroke length of the damper also can be controlled. If the stroke is controlled, then the forces are varying. The forces are varying. The force versus the displacement graph can be calculated. That is how they got that force versus the displacement, and also for various velocity, knowing this velocity and assuming that there is no loss, damping velocity versus the piston velocity can be calculated using this experimentally and also analytically, as well as we can calculate using the simulation. Earlier, I already shown the simulation work we have done and the practical work we have done. So these are all the assembly. This is the damper here. Then this is the upper. This is not the load cell. This is upper arm. This is the bottom top holder. This is the bottom holder. This is the MR fluid, and these are all the connector for this wire. This may be for coolant. This may be a fan to cool this one. Maybe it is getting heated up, and this contains the whole assembly. And this is external. This is the top plate, and this is the bottom plate to cover this one. And these electrical wires are coming and it is connected externally here. Thermocouple is given to measure the temperature. So this is the effect. Because they wanted to find out the temperature effect, they have put the thermocouple there, and they have drawn this temperature versus the damping force. Variation of the damping force in the, it's a beautiful graph. They have drawn time versus the damping force as well as the temperature they have got. It is can be clearly seen that if the damping force is lower, the temperature is higher for the, as the time passes by. These are all the images they have got at the particle, heat treated particle, and this kind of a study they have done at heat treating particle and tested how that is going to change the properties. This is a semi-active single degrees of suspension system. It is very similar. Now, the same analogy. In fact, recently, 1 week back, I have seen a paper they have developed. We are also having a collaboration with them, the Korean counterpart. Actually, they also developed. This is the same system. We can develop for this, this landing gear of the aircraft. They have developed this one, Korean people. And this is same technology, same concept, same mathematical modeling, same kind of a setup. We can also make for our Indian, Tejas and all for land. This one, this same principle here because this landing gears are now not having MR dampers. We can put the MR damper, and then this instability, especially during the landing, we face a lot of discomfort. That discomfort can be reduced by using the MR damper. These people also can write a proposal and can get a very good amount because people are now interested. Central government is very interested in drone technology, how to control the drone, stability and all using that MR fluid is a good topic. You can write, and my help is always available to all the people. So that is how this setup single sensor control system is. This again a damper, and then some actuation is given either by this some controller, and this is moved, and then NI DAC is used to take this the reading. They have used this accelerometer to calculate this. This hydraulic power pack, as I told, this one motor and a pump, and this will pump, and this is the inlet. This will actually move the damper in the various dimension, and we can adjust the input base excitation. Same problem. This is the input base excitation. This is the same problem mathematically. Otherwise, what we have done here, this is the same problem. They have done using this. Because we don't want to use such a smooth this one, we do not want to use such a smooth to and fro motion. We wanted slightly. We wanted actually very. It has to vibrate violently, not very nicely. If you put a hydraulic cylinder, okay, it will not vibrate because it is very linearly move very smoothly. But we want to show that it has to vibrate violently, then we control. That is why we have given this, cam arrangement, so that it will have a instability, more instability. And if you have more instability, and if you are able to control that instability or vibration of that with the MR damper, then it is good. That setup is same. This principle wise, it is the same. Here I am giving the motor and moving up and down. They have given this hydraulic cylinder move and up and down because that is available to them. So that is what that is for high power. We have demonstrated for low power because we are using only some few kilowatt motor. They are using the big hydraulic power. That's all the difference. But concept wise, everything is the same. So that is what is done there. That is what is done there. So that model, same, this quarter model, half model, these are all available. This vibration analysis, if you are interested, this is available. Quarter model available, quarter car model available in the Introduction to Mechanical Vibration by S.S. Rao. This actually, this all these solutions are actually available, and you have to make this wall and test it and prove that for different amplitude and different frequencies. Okay, then this what is the behavior of the damper. So that is what same earlier, whatever just now I explained earlier. Same thing, you have you disturb this mass, okay, and then you control it using the damping force. Damping, you disturb this mass and you control it by the, and they have controlled it only one. In our experiment, we have controlled it two because we have placed the primary mass and then we have designed the separate controller system. Just now I have shown, and this they have done it in a single setup. But here, like in your two-wheeler, it is just like your two-wheeler because it is also having a spring, and then this damper, and only this damper they have controlled. This damper they have controlled. This is fixed. They have done this control behavior. They have studied. This is this similar problem. The same problem can be used to prevent. Suppose if this is the primary mass and I want to control the vibration of the primary mass, then I can create another secondary mass, and I can put the damper here, and I can write the 2 degrees of freedom equation of motion for this one and equation of motion for this, and solve. That's what we have done for that DVA. And this is a single, this one mass, one spring, and one variable damper, like in our two-wheeler, that is done here. So you can see that sprung mass, increases, the vibration increases, and then how to reduce that vibration using the MR damper is shown here. Okay, at low frequency and high frequency. So also same thing. If this model can also be used for controlling the the suspension system, okay, of the four-wheeler. It also can be used as a suspension system in our landing gears. Concept is similar only. So here suspension of here we are controlling the suspension of the motor, the four-wheeler, because it is having a spring. Okay, then if it is a if it is a aircraft, then this is going to be your the landing gear. Landing gear forces are different, and therefore these designs are quite different, and their control is very different and difficulty. So that is what they have taken here. The same thing, they have a excitation table to excite this this one, and then after that excitation, you how this is going to dampen that vibration excitation. That they have studied for various frequency. You excite it with difficult. This is an exciter. You excite it different frequency, and for different frequency, how what current is required to absorb that frequency, absorb that vibration can be studied here. That's what suspension system studies. And then you can capture these readings using the DAC, the NI DAC. So these are all real-time studies. These are all the studies that are done. I have already shown very clear demonstration of the two-wheeler. Okay, these are all the studies we can do on the two-wheeler. Then instead of circular, we can use rotary things. These are all the things we can try. Not a big difficulty. It is there. For bike and all, we can try. Basically, it is a the suspension system, suspension spring. Either you can try for a four-wheeler, like along with the leaf spring and this damper, hydraulic damper, we replace this hydraulic damper by the MR damper. Therefore, this control becomes easier. And we have to design a control strategy to control this current and control the current based as a function of the speed. If the car is moving with certain speed, and what current I have to send to this MR damper so that this vibration is minimized. These are all the kind of a kind of a parameter people are interested. However, we cannot remove this suspension system. In fact, people can take this work because now people are coming with the electrical vehicle. In the electrical vehicle, actually people can try. We have not tried. Just some idea I am giving. People can try in the electrical vehicle replacing. Even in the two-wheeler, electrical vehicles are coming because even in the budget, Prime Minister has given a lot of importance and budget money for developing skill hub, and the NIT Calicut is also taking part of that. So a lot of money is available in that skill development. Under that skill development program, Prime Minister Kaushalya Yojana, this can be actually we can train the people and can develop such a kind of a low-cost technology for these two-wheelers, electrical two-wheelers. So such kind of a work is not so difficult, and always collaborative work from various faculty members and students is always welcome. And nowadays, inter college or inter university collaboration always works the best. So people have tried for machining. Actually, Professor Mohit La has developed, MR damper based. Actually, he has not developed. Actually, we are proposing to him to develop one MR based boring bar. So now they are developing a different kind of a boring bar. And during here, what we are showing is that simple machining, and you make the tool vibration can be reduced by putting a damper like this filled with the MR fluid, and it need not be so large. And even nowadays people are putting a small dampers in the tool. Just make the in the tool you make a cavity, so that you should see that the tool strength is not reduced, and you put this current coil here, small current, maybe small current, and you see how this vibration can be reduced. Such a kind of work people interested can do that and give it to their MTech and BTech classes. So these are all the result of that tool measurement. So this is commonly used for machining operation. Using a simple lathe, we can control the vibration using the MR based tool or MR based tool post. Using the vibration sense, vibrate oscillometer, we can calculate the forces, etc. Machining forces. Theoretically, also we can calculate the cutting forces, and then we can compare the accelerometer reading and the theoretical calculation and cutting forces, all three cutting forces using the dynamometer. Okay, so when the controllers are on, you see how smooth it is giving. When the controller is, there is no MR damper, probably this is a rough cut. When there is a MR damper is there, you can get a smooth cut. It is very evident here. Such MR fluid can be used. You see that whenever there is no MR damper, the vibration is very high, the oscillation is high. When the controller is on, and this is actually a lab test, and it can also be even fine tune, and this vibration is reduced. Because of this vibration, you will get a very clean surface, and a very lot of time is saved, and lot of machine life is also improved because vibration is there. The tool life is reduced, and also the machine life is reduced. Thereby you can increase the tool life as well as the machine life. People have tried this kind of a work. This work can be extended for milling. You can give this for drilling. All this kind of work is not being done. This kind of a work, simple work can be done, and either MR fluid can be purchased or it can be made in-house. This kind of a thing can be studied. Here, rotary MR dampers are also made by certain people, and this rotary arrangement is shown here. And this rotary arrangement is similar to this linear. This is only difference is this rotary arrangement, and you have a coil, and this is connected to this guy, and then there is a closure here, cap here. This cap is closed here, and this all these things are the input supplied here, and this the MR core and winding is there, and then you put the cover and put it here, and this guy is rotating, and this is the coil, and this is the wall cylinder body, and you supply this oil, and this is actually the rotor. By controlling this current, and this is oil, and this is the chamber, this is the oil hydraulic cable oil. This is, so once you give this oil, and this the force that is required to churn or rotate, it will be depending upon the frequency, like you are churning uh, the powder with some oils. And if I increase this current, then this becomes thicker, and that is difficult to this one. So if you want to say, for example, you want to use this problem for grinding the grains, suppose hard grains are there, that means I have to rotate more, that means more current. If it is a soft, I don't have to give the same current. If this soft, this is to be ground, instead of this one, I can use a grinder. Then if soft grains are there, like rice, etc., then I don't have to use a large current. Therefore, if I optimize, then this also can be used as a grinder. So something, not just this, all this can, ideas can actually be generated, because we have so many rotary motions in engineering, and all such rotary motion where the vibrations are required, where the controller is required, there where we can think of the MR based actuator or the controller. Of course, some development of the controller is some knowledge of the controller. This is the work of the Hemant Kumar. It is not our work. This work, similar work we have done, because torque sensor is available to them. And this is the rotary MR damper they have tested. This is the rotary MR damper. This is the stepper motor they have rotated. This is the bearing blocks they have supported. And these are all the couplings. There are 1, 2, 3, 4 couplings are there, and this is the DC power supply they have given it to for the rotary damper. This is the DC power supply where they can control give the current, and this is the inlet of the this connector oil. This is the coupling. This coupling is connected to this support, okay, bearing block, and this is a single shaft, and this is connected to the torque sensor to know value the torque reading. Then this is driven by the stepper motor. Because it is a small, therefore they wanted to control the steps probably. That is why they use the hybrid stepper motor. Also, you can use a servo motor. Today, servo motors are also not that expensive. If money is available, some grant is available, you can use the servo motor with the variable frequency controller and controller. Then you can control the speed for various speed, and you can study this kind of a rotary damper. This is actually available, and these are all published work. That is why I'm showing. These are all published by Professor Hemant Kumar. This work is done by them. Therefore, I'm retaining his name on this slide. So this application, this kind of a configuration people have tried. We have also tried 1 or 2 configuration that I have explained in a detailed way. So this kind of a type, D type, disc type we already used. This is the disc type dampers that we have developed at NIT Surathkal. That is a disc type only. What we have developed. This is the disc type of. This is a disc type of. This is actually a disc type of brake only we have developed. Okay, here this is a disc type of brake only we have developed. So this type of brakes, and these are all different various types of brake design. One can try for high torque applications. There are various things, but we have to see how to keep the bearing and how to avoid the leakage. That and all is a big so that has to be taken care actually while doing this, while designing and fabricating it. So brake I already explained earlier. This is the coil, this is the MR fluid, and this is the disc. And if you energize this coil, this becomes a solid and the brake is applied. Then this and this will not move. That means this brake, this disc will stop. That is the idea. That detail we have already done. And this is how this ring seal is used to avoid the leakage. And we have found that ring seal and all will not work. And we have used the white on seal, and that itself is costed around 10,000 rupees for that kind of a job. So rheological brakes, many people have done this kind of a work. So here is one casing cap. This is the rotor disc, and this is one right side, and this is the left side, and this is the bobbin on which the winding is there. And when you energize this fluid, the fluid between this rotor and the stator will become solid, and the rotation is prevented. That is how this setup. This is the coupling. There is a variable dimmer to control the speed, and this is a flywheel. Once the flywheel will store the energy, and then whatever the flywheel stores the energy, and that energy when you apply the brake by increasing the current, whatever that energy that is stored, that much energy is absorbed. That is how we can equate this. Theoretically, you can calculate whatever the energy that was there in the flywheel, that much energy is braked using the MR brake. Also, that can be theoretically calculated. But here we have the torque sensor. The torque sensor itself can actually indicate when it is about to brake. Then torque sensor can indicate the torque, and then we can calculate by increasing the speed per given current, what is that braking torque that is required. We can draw like this for various type of fluid. So this is done a long back, and we have started actually with this kind of a primitive work in NIT Calicut, and then year after year we started to develop this one. This kind of a work is already done by Professor Dwivedi Sahab in NIT Guwahati. Actually, this work is not exactly like this. This, if you want to control this is also can be done by the simple things only. These are all. So you have two plates, and here they have used the bottom plate. You can also use it for composite. Also, you can. This is also a good PhD work. You can use a 2 MMC plate, and between MR fluid can be used. And by varying the thickness and the functional material, you can actually study what is the vibration of this, because this is very easy to actually fabricate. If you have a composite layer, composite material, or steel layer, or aluminum, actually the way the Saab has done with the aluminum layer, if I'm not wrong, aluminum plate, 1 mm or 1.2 mm, and then you use the MR fluid, then you change this current. Okay, either they must have used this permanent magnet. In fact, we can also develop some system for electromagnet. Then you apply, and this vibration of this composite plate can be controlled by controlling the current at various points. And mode 1, mode 2, mode 3, how this mode 1, mode 2, mode 3 can be controlled, can be simulated, and can be controlled very easily. This work I'm planning to give it to the manufacturing machine design student who also got Tata this year. So that I'm just planning to give this work and study much more on this work. So this vibration of the structure can also be done with the this one, magnetoelectrical beam. This is also done by Hemant Kumar sir at his institute, NIT Surathkal. So what they have done is this that the plate, okay, this is all effect sensor. This is a sandwich beam. Then what they have used the exciter. Yeah, they have fit this accelerometer. Then they have placed this permanent magnet. Okay, permanent magnet they have placed. Okay, permanent magnet. Actually, this permanent magnet need not be placed. Improved version of this can be done here by putting the winding here only, okay, at both the side, and then you can study this winding here, here, or full winding, 1/4 winding, 1/2 winding, like this. Because if this is a cantilever beam, at the vibration, the deflection will be more at the end only. Therefore, the deflection at the end has to be controlled. So we need not have to place. I'm just an idea I'm giving. Need not have to place the magnet full length. It can be stored here itself, and then it can be, that work can be extended. Actually, this can be a good work for PhD for various composite, various material, various functional material. You can control and you can excite. They are exciting using the impact hammer, and then they after that they change this current, and then they will study the vibration characteristics. For example, for this composite material with the MR. That is how this can be used. This is software used to capture this vibration pattern. This, we also have this software at NIT Calicut to capture this. It's a kind of a simple work which will not involve lot of money for PhD. Okay, because PhD students will have to have family. So this kind of a small setup which involves both simulation work, the analytical work, and some good work can be done, and you can take a metal composites and try all this kind of, or even polymer composite, all those things can be extended. This is one work, they have one very good work they have done, Hemant Kumar sir, and now that can be extended to many work, and good paper can be produced under this. So that is the beam setup. That is just I have told you, this is a vibrator. That is they shake this one by the electrodynamic shaker for this cantilever, and this will vibrate, and then they will capture that vibration without the magnetic field, and then they increase the magnetic field and study the MRF behavior, how that vibration can be reduced. So this is what I have in my slides. We have actually come to the end of the slides, and I am very grateful to all of you for patient hearing, and this was a very long lecture. I understand it is very difficult to hear, for especially the faculty members to hear such a long hours, and I appreciate your patience, and I wholeheartedly thank organizers organizers of this workshop, RAMM, and I wish all of you a great success in your future endeavors. Thank you very much.
Thank you, sir. That was a well explained, detailed, and exhaustive session of yours. Now the floor is open for question and answer session. Yeah. I request all the participants, if you have any questions, please type it in the chat box, and you are also having the freedom to please unmute yourself and ask your question to the guest speaker.
Please ask, and you can type as
any questions from the participants. Please type, or you can also unmute and ask.
You can unmute and ask, no problem. If you're having mic problem, you can type in the chat box. I will try to answer. This is actually a very simple, it does not involve a lot of things. It involves only preparation of the MR fluid and a little setup. That's why we started this kind of work. And I request all of the participants who are guiding the students, and please try this to devise some small work, and a good paper can be published.
Sir, I have one question.
Please.
Since I worked on MR fluids.
Yes, sir.
This was just a general question which I wanted to ask.
Yeah.
The recent earthquakes in Turkey and Syria.
Yeah.
More of concentration has come towards like where the next earthquake will happen and how to resist the destruction of buildings and assets.
Yeah.
Can this MR fluid be used for dampening vibrations, earthquake vibrations?
Yeah, this is in fact a very, very good question. This is structural damping is a separate subject altogether. For example, in Japan and all, this is actually a very good question, a very interesting question. In Japan and all, the people we don't do it in India because most of our places are very safe. But in Japan is very prone to earthquakes. Okay, and every structure when they build, they will use what is known as the structural damper to dampen, and in which these pillars, the very pillars, if they vibrate, they can accommodate this vibration. They will not fall, and if there's a big structure, they will not fall, and actually it will simply vibrate and dance a little bit and come to the stable because of the structural damping. They will actually provide a damper. Okay, even I have seen in the bridges, etc., in Japan to provide this kind of a damping. And this MR damper for structural application, I have not come across, honestly, I have not come across, but this kind of a structural damping, because very huge amount of force comes into the structure, and now hydraulic dampers are in place, especially in the case of bridges, and where transfer the bridges, like in Malaysia and Britain and all, they have this, the whole bridge will move to one side and this ship will pass away. Such kind of bridges, this kind of when you move this bridge from one half to another half to open this big ship, then there will be a vibration, just like a cantilever problem I have shown, and that vibration can be minimized by this kind of structural dampers. Of course, this earthquake, this one is there, structural damper. If you type in Google structural damper in Japan houses, you will get a lot of material. These are there in the in place for quite a long time. But I do not know really whether MR damper is used. But people have demonstrated this kind of a dampers, MR dampers for structural work also. Like, I will show you the diagram just. Such this one, you see this paper in 2005. Are you able to see this one, the slide number 8?
Yes, yes,
yeah, yeah, visible. So this is a shaker, this kind of a structural application. These are all the building with the floor M1, M2, M3. It requires a huge, a lot of huge this one. And Japanese, they build a very small structures, not a huge building. And this kind of a vibration, earthquake is nothing but the movement of these floors that can actually be controlled by this kind of a structural damping. This kind of a people have done, and papers are available in 2015, much earlier. This kind of work has been done for structural work. I had to read this paper. I have just mentioned here. I have not read this paper fully. What kind of a structure, what kind of the load, what kind of the, the load this is able to resist. That is very interesting. That we will read and understand how much is the force they are able to dampen it out. I have not read this paper, Enric paper, but it is very interesting to know that they have done this kind of work. In fact, people have developed, for example, that Indian Army, when you shoot a gun, that gun recoils, right? It's also a structure, right? The gun hole is a very big structure. If it recoils, then it may go and obstruct something. Such kind of iron dome, etc. It recoils. That recoiling also can be controlled using the MR damper. In fact, I proposed to the DRDO. Then they have not shown this interest for this Indian guns. Then I stopped it. As MR damper can be used there also for this gun recoiling. Structural, yeah, structural it is used, and this moment of the the floors, etc. Can be minimized using this kind of a dampers. This is in place. The MR dampers may not be in place in Japan, but this kind of a conventional dampers for the houses are there in the bridges and the structure, civil structures.
Okay, sir. Thank you for clearing the doubts. Sir, we come to the last section of the program today.
Yes.
And I request a few participants please give their experience, share their experience about the 3-day online faculty development program. So I request Dr. Ravichandran ji to please share his experience. Ravichandran sir, are you there?
Yes, sir.
Can you please
Is it
share your?
audible?
Yes,
Is it
sir, you
audible,
are
sir,
audible.
properly?
Loud and clear. Yes, sir, loud and
Yes,
clear.
sir.
Yes, you are audible.
Thank you. It is my privilege to express my view and also the opinion in the form of feedback on these 3 days online faculty development program, that is recent advancement in materials and manufacturing. First, at the outset, I'll thank the management and the staff of the St. Joseph Engineering College, so Mangalore, providing an opportunity and create a platform to attend this FDP program online mode. Secondly, with respect to the organizing committee, so Professor Sriranga Bhatt sir, Professor Raju K, and Professor Kenyut Sherbin, and Professor Noel Deepak, I really thank on behalf of all the participants choosing the right topics related to the title, the advancement in materials and manufacturing as a different modules, starting from the sustainable manufacturing, investment casting process, smart engineering, micro machining, even 3D printing, and lastly the smart materials in various engineering applications. At last, so the resource persons or the speakers, so the selected speakers are the resource persons from the various national importance organizations. In their busy schedules, they came in this platform and expressed their views in their expertise areas, especially showing their the facilities available in the labs in their institutions, and also we observed. So most commonly we are observed all the participants in this particular workshop, faculty development programs, we are from affiliated colleges and also the some of the private universities. So always there is a gap between some of the national importance institutions and also these affiliated colleges. So we agree for this, so that gap can be fulfilled by this arranging these type of FDP programs in various fields. um, I sincerely thank all the management committee and organizing committee and all the speakers and also research persons who express. And we are just recently we are completed our research what to do next, what in which direction we have to flow. So all these questions arises in our mind. So finally, so this is the right time we are attending and worthy the time spending worthy in this type of faculty development programs, and we are going to carry forward in the future in our either in the form of research or in a teaching learning practice or the development of the curriculums in our universities and the institutions. Thank you very much for providing an opportunity to give the feedback on this particular faculty development program. Thank you very much. Thank you, one and all.
Thank you, Dr. Ravichandran. I now request Dr. Vasant Kumar, HOD of BIT, Mechanical Engineering Department, BIT College. Dr. Vasant Kumar, sir, can you please share your feedback?
Good afternoon. Hello.
Yes, sir, you can present.
Yeah. First of all, I would like to thank organizing committee, Sriranga Bhatt sir, Raju sir, Servin sir, and Noel Deepak sir for organizing such a wonderful faculty development program and recent advancements in the materials and manufacturing. Really, it was a very interesting and a very useful topic. All the research scholars and all the faculties from various institutions. Actually, it was really very interesting. Why? Because most of the research persons from NIT and IIT. So yesterday, Saman sir and Professor Somashekar sir was shown some very important laboratories. Really, it is very useful. Those pursuing a PhD, also those completed to improve their research. Also, I thank management and the Department of Mechanical Engineering, SJEC, for organizing such a beautiful faculty development program. Thank you. Thank you, one and all.
Thank you very much, sir. Thank you so much, sir. Now I request Dr. Shankarappa K. Kalgudi. Can you please share your few words on the feedback?
Okay, sir. Listening, sir? Hello?
Yes, sir. You're audible.
Yes, sir. Good afternoon, all. Sir, first of all, I thank to the organizing committee, especially for the Raju K. sir, as well as NIT Serving and Naval Deepasri and Sriranga Bhatt sir, for organizing such a wonderful as well as informative FDP, which is needed for all our engineering faculties, sir. So, as we have organized 3 days FDP from 13 to 15, the so many topics you have selected are very relative. For example, sustainable manufacturing, investment casting process, smart manufacturing, micro machining, 3D printing, smart materials. Out of all these three, whatever the topics which I have very liked are smart manufacturing, micro machining, 3D printing, and smart materials. From this, I have got a lot of information to proceed my research work, sir. So once again, I thank to all the organizing committee and thank you one and all, sir. Hello.
Thank you very much, sir. Thank you, sir. Any other participants would like to share your experience? You are welcome. You can please unmute and share it. So nobody wants to share. Okay, we'll move to the last part of the program. I request Dr. Raju K, Professor and convener of this faculty development program, to please present the vote of thanks.
Good afternoon, everybody. As we have come to the end of this 3-day FDP program on recent advancements in materials and manufacturing, first of all, I thank Professor Jagadeesh for accepting our invitation and giving a presentation on smart materials, a detailed presentation on smart materials. Thank you very much, sir.
Thank you,
In fact,
sir.
I thank all the speakers of our FDP in their absence for their wonderful presentation on different topics on materials and manufacturing. At this juncture, I would like to thank our director, assistant director, principal, and HOD for their constant support and help in arranging this FDP. I thank all the participants for registering and attending this FDP. Without your active participation, I think FDP will be incomplete. Thank you for making this FDP a grand success and fruitful one. We will email your participation certificates to all the attendees in a week's time. And also the FDP material we are collecting from all the speakers. Once we collect it, we'll email the same to all the participants. Thank you one and all for your wonderful participation in this FDP and making this a success. Thank you.